So today we're going to be talking more about partial differential operators and the use of distributions in the solution of partial differential operators. Remember, we've gotten some results about getting the existence of fundamental solutions, and today we're going to do something a little bit, do this thing with so-called approximate fundamental solutions for parametrices. There's a result that I skipped earlier, or I skipped the proof of earlier, but I think it's worth doing, so I'm going to do it now because some of the results we see today will run along the same lines. Okay, so back to when we were talking about regular homogeneous distributions. There was this result in 2.4 that if K is a regular homogeneous distribution of degree lambda, then its Fourier transform is also a regular homogeneous distribution of degree negative d minus lambda. So most of this some of this we've done already, that if you have a homogeneous distribution of degree lambda and you take its Fourier transform, then you get a homogeneous distribution of degree negative d minus lambda. Right. So the thing that this is talking, the main difference here is this word regular. Right? So that is, if K agrees with a smooth function away from the origin, then K hat does also. So that's the main thing. Okay. So let little k denote the function that big K agrees with away from the origin, and we're going to break big K into two parts. Let eta be a infinity function that is supported in unit ball, and such that eta is 1 in the ball of green is a half. Okay. So it's this bump thing here, and then drops off. So this bump function, and then we're going to split k. Let k naught be eta k, and let k1 be 1 minus eta k. So this is a product of distributions. We're multiplying a distribution by a function. Right? Okay. So then, sort of obviously, k1 agrees with 1 minus eta little k, right? K1 is clearly a regular distribution, right? Here's the function that it agrees with. And also obvious, k hat equals k naught hat plus k1 hat. Okay. So what we need to show is that that these guys are regular. These guys agree with functions away from the origin. Okay. So okay. Well, this thing we don't really have to worry about at all because k naught is compactly supported K0 is compact-reducible. So we know that K0 hat is a C infinity function. That we showed earlier. So that actually is a C infinity function. So it's it's a regular distribution. So the main thing that we have to worry about is this K1 hat. So okay. So okay. So outside of the unit ball, we know that K1 agrees with little k. Right. Outside of the unit ball, we've got 1 minus 0 times k. Right. So the alpha, any derivative of k1 then is a homogeneous function. Right, so this k, remember, is a homogeneous function of degree lambda. Right. So when you take derivatives of it outside of the ball, this thing is also a homogeneous function of degree lambda minus the size of alpha. When you take derivatives of homogeneous functions, you get again homogeneous functions of lesser degree. So it's big O of it'll be controlled by it will be controlled by this. Okay. So so that tells us that if we look at the Laplacian to the nth power applied to x alpha k1, that thing is going to be of order. It's going to be big O of x to the lambda plus 2n. Why do we care about that? Because observe now. Observe just by the usual interaction of Fourier transform and the regular differentiation and multiplication by polynomials, that if we take Laplacian to the n of negative 2 pi I x to the alpha k1, and take the Fourier transform of that, then we're going to end up with negative 4 pi squared c squared to the n, the derivative k1 hat, the alpha derivative of k1 hat. Just by the normal properties of the Fourier transform and differentiation and multiplication. Okay. Okay. So okay. So what's the point? Sorry. So the point is that this thing for large n, this is in L1. Right? For large enough n, this thing will decay sufficiently fast, right? And then you'll be in L1. And being in L1 implies that your Fourier transform is continuous. Okay. So if we take large enough n, we know that this guy here is a continuous function, right? And that tells us that that this guy here is a continuous function, right, divided by this thing, and so it's going to be continuous. It's continuous away from the origin. And then there is an exercise in the text, so my exercise 2. This implies that k1 hat is C infinity away from the origin. Right, which is what we wanted. Right, we wanted to show that that this thing was also also regular. Yeah.
The step from now observed to the next line.
Yeah. So the point is that this thing for big enough L, for big enough n is in L1, its Fourier transform is continuous, right? You divide both sides by this, right? You get this you get a continuous function over a function that's continuous away from the origin, right? So so the quotient is continuous away from the origin. Okay. Okay. Other questions? Okay. So that's a little bit of a digression, but the pattern of the argument we will use a couple times today, at least once. Any questions? Any questions? Any other questions? Okay. Okay. So we're going to talk about parametrices. So here's the definition. You have a partial differential operator. With constant coefficients. A distribution Q such that LQ equals, the Dirac delta plus R for some R in the short class is called a parametrics, or an approximate fundamental solution. So this is, something like a fundamental solution, but not as good, right? We don't get, fundamental solution. We would get just a Dirac delta, but here we get Dirac delta plus some short class function, plus some error. And the error is, in some sense, small in that it rapidly decays at infinity. But we'll see that actually having a parametrics is actually a pretty good thing to have. So our ultimate goal today is to get to this theorem. Our ultimate goal is to get to the following theorem: that if again you have this L and you have a distribution on some open set omega in RD, and you have this distribution solves LU equals F. So it solves a problem for some F infinity. If L has a regular parametrics, then in fact U is a C infinity function on omega. Okay, so the existence of a parametrics, or a regular parametrics, does something good for you. If you have a solution, right? If you have a solution and the function here is C infinity, then in fact the distribution that solved it is a C infinity function. Okay. So the point is that you know when you solve partial differential equations, you can solve them in the distribution sense. But maybe you would like to have, in some sense, you would really like to have a function that solves your partial differential equation, right? And so this is what allows you to actually, this says, in fact, if you have a regular parametrics, then you actually do have a function. Okay. So you do have a smooth solution to your equation. So this will allow us we will have to step into the world of distributions, but this allows us to escape backwards to where we want to be in the world of functions. Okay. So other part of the so let me erase this. So a couple more dimensions. The parametrics Q is called regular. It's called regular. If it agrees with a C infinity function away from the origin. So this is normal. Obvious definition. Another different definition. Let L be a partial differential operator of order m. So it's going to be some combination of derivatives all of order less than or equal to m. If there exists a C bigger than 0, such that the characteristic polynomial P if there exists, if P is bounded from below by some constant times the size of C to the n, then we call L elliptic. So these sorts of operators are called elliptic operators. And what we're going to show is that every elliptic operator has a regular parametrics.
Is there a geometric interpretation
Of this statement?
Yeah.
So, yeah, I honestly I don't have a good one. In the text, they do the following. Being elliptic is equivalent to saying that the part of P, which is homogeneous of degree m vanishes only at the origin. Part of P that's homogeneous of degree m vanishes only at the origin. Okay. I have to say that that's sort of opaque to me as well. But does anyone have a better sense of this? You know, what does it mean? What does it exactly mean to be elliptic? Let's just stick with this. In any case, we'll be able to, we're going to show that if L is elliptic, then L has a regular parametrics. Okay. So, let me say it like this. Okay, so it's the proof. So, L. So we know satisfies the condition, right, for all C bigger than outside of some radius. So here's the idea. Let gamma be supported in that place where we have the lower bound for P, such that gamma is equal to 1 for all large C. So right, it's right, some sort of the opposite of a ball function. So take this and spin it around. Then take Q to be the distribution, the temporal distribution such that Q hat is equal to gamma over P. Gamma over P is a temporal distribution, and its inverse Fourier transform also the distribution. Okay. Then, if we look at LQ hat, you get P times gamma over P, right, which is of course gamma. And you write that as 1 plus gamma minus 1. Now, gamma minus 1 is function, right? And so, so it's r hat for some r in the short class. Okay, so that's to say that LQ hat is equal to 1 plus r hat, and that's to say that LQ is delta plus r. Okay, so you see how we're using the ellipticity, right? In the case of remember when we were doing this sort of thing for fundamental solutions, the main trouble was that, we wanted to avoid zeros. We wanted to avoid zeros of the characteristic polynomial so that we could play a similar game, right? And here, ellipticity allows us to do that, right? We can divide by this thing because of the elliptic condition. So that's at least part of it. And we're not done. We still need to show that that this Q is a C infinity function. So right at this point we have that this thing is that Q is a parametrix, but not a regular parametrix. So we still need to show that Q is in C infinity. So again, as in the previous proof, we make an observation using the Fourier transform. If we take -4, so it's not exactly, but similar to the previous group, we look at the Fourier transform of -4 pi squared plus 5x squared n times the derivative is d beta of x. And you end up with the Laplacian to the n 2 pi c beta gamma over p. There's an estimate here that I didn't check, but I'm just going to use it. Okay, so one can derive the estimate that if you take the alpha derivative of gamma over p, then it's controlled by some constant times c negative minus the size of the index. So from that, that gives you that the right-hand side, let's call this thing star. The right-hand side of the star is bounded by some constant times c to the minus m plus minus m minus beta. Sorry, minus beta minus 2m. we note that further, the right-hand side is bounded in C less than 1. The point is that why does this happen? Why is it bounded in C less than 1? Well, the point is that we're using this gamma, right? The trouble is that we don't. The main thing is that we want to avoid this thing becoming 0, right, or becoming arbitrarily small. But we're multiplying by gamma, and so gamma cuts that all off, right? It says we're only going to stay. By using gamma, it says we're only going to stay in the place where the polynomial is bounded away from the origin. Okay. So at the very least, this thing is a smooth function, right? This thing is a smooth function, and being smooth on a compact set gives you bounds on it. Right? You're taking this function and you're multiplying it. You're differentiating it, right? But this function is smooth, right? And it's smooth on a compact set, so it's bounded. So the point is that gamma keeps us safe, right? Keeps us away from the zeros of P. Okay. So from then on, it's basically the same argument. You say, well, look, we have this thing that is, if we take n big enough, if we take n, and we have this thing so that if we take n big enough, then it's integrable, right? So for n large, the left-hand side is integrable. Right? And the right-hand side is the left-hand side, of course. For n large enough, the right-hand side and thus the left-hand side also is integrable, right? And so you take the inverse Fourier transform and you get a continuous function, right? So let me see. The right-hand side is integrable, so the inverse Fourier transform of the left-hand side is continuous. Right. Then, by the same argument as before, by exercise 2 again, by exercise 2, we're done. So the point is that one gets that this is continuous for all beta, and that forces the function to be that forces Q to agree with the C infinity function. That guarantees that Q is regular. Any questions? Sure. No? You're looking at me. I'm not sure why you look at me. I know I need a haircut. I just said it at the time. I'll cut it this week. For the longest time, I cut my own hair from like age 18 to like mid-30s or so. Then I became a professor here, And I said, okay, well, maybe I should look more professional. And I started getting my hair cut. But now I'm a tenured professor, so I think I'm going to go back to cutting my hair. It saves money too. Yeah, when I first cut my hair, this is completely irrelevant, but when I first cut my hair in college, I was so embarrassed at how I looked that I started walking to classes. Instead, I ran from class to class. Like I get out of one class and I just run to the next class and stay in the classroom. But even so, I kept on cutting my hair.
You didn't think that more people would notice you if you were running?
Actually, it so happened that somebody said, a good friend of mine said, you know, today I was walking around and I saw this crazy looking guy run by me, and that was you. I saw this, you know, it's like, I saw her, I was like, what's this, who is that insane looking person? Oh, it's my friend, Winston. So yeah, I guess I could actually draw more attention that way. Either way, the embarrassment was shorter, I guess, if I ran.
Why didn't you just wear a hat?
Hats. I don't remember anybody wearing hats back then. You know, like baseball caps, people wearing baseball caps and stuff sort of came later. People did not wear hats. It would have been even stranger. So I didn't quite make this connection until just now, but actually that friend of mine who made this comment about this crazy guy who was running around, later got his haircut while drunk, and he ended up with a mohawk and wore a bandana. Yeah, I think I wasn't there, but the eating club, and the eating club is just a place. It's sort of like a fraternity, I suppose. Everybody in your junior and senior years joins an eating club, and they have these parties or these sort of events. And one was, you know, get your hair cut at this party. And so the way my friend told it, he sat there, and then the hair cutter just like shaved up one side of his head, and he said, "What are you doing?" And she said, "It's too late now." She could not do this. Yeah. Yeah, maybe he was not drunk, but it was at one of these parties. Yeah. He later became an actor, actually. Although now he's going for his PhD in psychology. Okay. Those were the good old days. Okay, so here's something useful. And it's listed as a corollary, but it's not really a corollary. Let L be, so in the text they say let L be an elliptic operator, but actually it's simply an operator with a regular parametrics. So an operator with any regular parametrics. Then, given any epsilon greater than 0, there exists a regular parametrix q's of epsilon with subordinated all radius epsilon. So really the corollary is thus it's true for elliptic operators. Okay. So this is actually a lot simpler than you might think. The proof goes as follows. I say, well, again, let's say that let's take the Parametrix Q. So we let A sub E be, again, a compactly supported smooth function such that it's supported on the epsilon ball, right, and it's equal to 1 on the half epsilon. So that the support is contained in the epsilon ball, and this guy is equal to 1, constantly equal to 1 on the half epsilon ball. Okay, and then we take Q sub epsilon to be n epsilon times Q, and that turns out to be a parametrix, which sort of makes you believe that the parametrix is a very, very loose construction. Right? Well, let me show you. So this Q will work. Right? So we need to show that this Q epsilon is a parametrix. Okay. So consider L, the operator applied to n epsilon Q minus n epsilon L. So what's going to happen is that you have this differential operator applied to a product. Right? You have this differential operator applied to a product, and so using the product rule, right, you're going to get a bunch of terms out of this thing. Right? You're going to get a bunch of terms, but then you're subtracting off n epsilon times LQ. So what that does is it subtracts off all the terms that involve the function eta sub epsilon. Okay. So all the terms involving eta sub epsilon will be gone. And the only things that will be left in this expression are the things which involve derivatives of eta epsilon. Okay. Like the only terms involving eta epsilon itself are going to be contained here. In fact, these are all the terms involving eta sub epsilon. Okay. So when you subtract that off, this thing has no terms involving eta sub epsilon. It only has only derivatives of eta sub epsilon. But you notice that the derivatives of eta sub epsilon all vanish in the epsilon over tuple. Right? So this thing is a so these would all vanish in the epsilon over tuple. Right? And so so what does that give you? That gives you that this thing is a C infinity function, right? Remember that Q is a regular parametrics, so it's a C infinity function away from the origin. Subtracting off that term guarantees that we stay away from the origin. We stay, epsilon over 2 away from the origin, and so this thing actually is a function. Right? So this thing is a function. Further, because of the support of eta epsilon, it's supported in the epsilon ball. So it's a compactly supported smooth function, supported in the epsilon ball. Let's say that that guy is called F. So we get that this thing goes out. But then, using the fact, now let's use the fact that Q is a parametrics. So we get negative eta epsilon delta plus some Schwartz class function. Right? But that's just delta plus eta epsilon times r. Right? So that tells you that L of our Q epsilon, L of our Q epsilon is going to be delta plus F minus n sub epsilon r. Right? But these are all Schwartz class functions. F is a compactly supported smooth function. It's in the Schwartz class. R was in the Schwartz class, and we're multiplying by a compactly supported smooth function. Right? So this thing is also in the Schwartz class. That tells us that this thing, actually, Q sub epsilon, is a parametrics. And a right-hand regular. Okay, so let's see if we can get the theorem, the main theorem of today. Okay, so here we go. L is the operator. In the proof of this theorem, we will need these compactly supported parametrices that we just read. Say that U is a distribution given on an open set omega, such that LU equals F for some infinity. L has a regular parametrics as L has a regular parametrics. Then U is a C infinity function on omega. Now I remember, my friend was not drunk while he got a haircut, but he got drunk after getting a haircut. That's the story. And Okay, right. So, let B be any ball, be an arbitrary ball of radius rho, such that its closure lies in omega. We'll show that u is a C-infinity function on B. So we'll show that basically for any ball whose closure is in omega, that u is a C-infinity function on that ball. So here's how we do it. Let B1 be a concentric enlargement of B. So you have your omega, you have some ball, and you enlarge it a little bit. So that rho and then rho plus epsilon. B1. Again, choose it so that B1 bar is contained in omega. And as we've been doing over and over today, take a cutoff function so that eta be a compactly supported cutoff function such that eta is equal to 1 in a neighborhood. It's called n, the neighborhood n of B1 bar, and such that the support of eta is contained in omega. So we have some n around here. And the function eta is 1 on that neighborhood n. Okay, so let now u1 be eta times u. Then u1 and L1 are both compactly supported distributions. And LU1 is F in that neighborhood. We know that LU is F. Right? As long as we stay inside the neighborhood where eta is 1, where LU1 is LU, which is going to be F in the neighborhood. So, sorry. They call this thing F, capital F1. This thing agrees with a C infinity function, little f1 of complex in a smaller neighborhood. Sorry, give me 1 second to make sure I satisfy. Sorry. Does that make sense? I'm not sure that I'm a little bit troubled by this statement actually. So what's the point? You've got you start with a U and then you hit it with N. You hit it with eta. So eta is 1 on a neighborhood of the closure. Eta is 1 on a neighborhood of the closure of B1, right? L of U1 we call F, capital F1, right? That's on N, right? So this thing on N, L U1 is equal to little f. Okay. L U1 is equal to little f. Okay. Is equal to little f. Okay. When we say that it agrees in a smaller neighborhood of B1, it agrees with some function, of compact support in a smaller neighborhood of B1. So I'm thinking that I think that just means that F1 could be eta times F, right? You take eta times F, you get F1. You're just cutting off. You're just trying to make a version of F that is compactly supported in a version of B1. So I think taking F1 to be will do it. Yeah.
Would you need a smaller neighborhood if F was eta?
Yeah, I guess so. But then, okay, so you take some different eta. Okay, eta 2. Right. because you can create this function that's, you can create this function that's equal to 1 in a neighborhood of V1. You can create one that is supported in a small neighborhood. Anyway, it's possible. It's possible to do. Okay, so I think that's okay. So what we're going to do is show that this U1, we're going to use the compactly supported parametrices from the corollary to show that this U1 agrees with a C infinity function on B. And that will tell us that, that U, because U is equal to, if we look on B, then U is equal to U1 on B, then U will be a C infinity function on B. So let Q epsilon be the parentheses, the regular parentheses from the corollary. Okay, so they're supported in the epsilon form of the arrangement. Now, observe, if we look at Q epsilon convolved with our U1, well, we can pass the differentiation over to the other guy. That gives us U plus the error function involved against U1, which gives us U1 plus our epsilon involved with U1. This thing is, you're taking you have a distribution of compact support. And you have a Schwarzschild function, and you're taking the convolution, and so that gives you the C infinity function. Okay. If we look at this thing again, from a slightly different viewpoint, say, okay, well, this is equal to Q epsilon convolved with F1, which we can write as Q epsilon convolved with little f plus Q epsilon convolved with F1, big F1 minus little F1. Remember that F1 is compactly supported. So again, by the same reasoning as here, we get that this is in C infinity. Right. You're taking a Schwarzschild function convolved against the distribution of compact support. So this is in C infinity. Or it's a C infinity function. And then you notice that sorry, there should be a composition here. The support of Q epsilon convolved with F1, capital F1 minus lowercase f1. Do you remember we had this result earlier that says that the support of a convolution is going to be in the set-wise sum of the supports, right? Is contained in the set-wise sum Now this thing here is contained in the epsilon ball. Right? This thing here is contained in the epsilon ball. So that means that this, what we get here is the epsilon neighborhood of the support of f1 minus little f1. Right? Okay. So now f1 minus capital F1 minus little f1 vanishes in a neighborhood of B1 hat by construction. Vanishes in a neighborhood of B1 hat. So that tells you that this convolution is vanish in B. Right? B was inside here. B was inside here, and this length here was epsilon. Right? B1 was the epsilon fattening of B. Right? Since f1 minus little f1 vanishes on a neighborhood of B1 hat, we know that Q has to vanish, that the support is contained, that the support of Q1 convolved with that thing, convolved with the difference, stays away from B. Right? So this guy vanishes on B. So putting these two sides together, what you get is that, so here we've got Q epsilon. We have this. This and this. Putting these two sides together gives us that U1 equals Q epsilon equal F1 plus, minus R equal epsilon involved with U1. Maybe we should write the all sigma. Plus Q epsilon involved with F1 minus F1. Right. So on B, well, this thing is 0. Right. On B, this last term is 0. And these first two terms are C infinity functions. Right. These first two guys are C infinity functions. And so that tells you that U1 is a C infinity function on B, and thus U is a C infinity function on B. So that gives you that in fact U is a C infinity function on omega. Next time we'll talk about Calderon-Zygmunt operators. It'll be more fun next time.